This video explained the decompression point in developing the load moment interaction diagrams. Now we are working on the decompression point. In the last video we talked about the squash load points. Now we are going to use clause 10, 0.6, 0.2, 0.3 for decompression points. So the decompression points, that's saying that decompression point is calculated taking the strain in the extreme compressive fibers. So this is extreme compressive fibers. Extreme compressive fibers has a strain 0.003, that is written here, and strain in the extreme tensile fibers equal to 0. So the strain in extreme tensile fiber is taken as 0. So the strain diagram is shown here. It's basically saying that your neutral axis is sitting here, and the strain diagram is shown here if your neutral axis is sitting here. Now first of all, let's calculate the force in the concrete compressive region. Now if I draw the stress diagrams, because it says that the rectangular stress block should be used to calculate the concrete forces. Now that is given in clause 10, 0.6, 0.2, 0.5. So if I just turn the page over, I would have this stress block. It's the same similar stress block that we done in the beam examples, where you have this alpha 2 epsilon, that is the stress in the concrete. You have height of the stress block, which is given as gamma KUD, and we can calculate alpha 2 first. Alpha 2 equal to 0.85, take away 0.015 epsilon, and that should be greater than 0.67. Now in this case I can just work it out. 0.55 take away 0.015 times 40. Now 40, that is given the concrete compressive strength in the questions. 40 is 40 megapascal concrete compressive strength. I substitute that. It gives me the answer 0.79, which is greater than 0.67. Therefore is okay. Now this gamma equation is also given in this clause. 0.97 take away 0.0025 times epsilon. Substitute epsilon as 40 megapascals given in the question. Just now we look at that, which is gives me 0.87, which is greater than 0.67, so therefore it's okay. Now Ku, please note the neutral axis is sitting here. If you remember that in the bending equations, where your neutral axis is here, you can have dn value divided by d. It is your dn divided by d, it is your 1. But in this case our neutral axis is sitting at the tensile side, so all the dn value, this should be divided by d, so that is 1. So alpha 2 epsilon gamma KUD. So the force in the tensile, force in the concrete compressive region is calculated as stress times area. Now the stress in this concrete is alpha 2 epsilon, that is the maximum stress, times the area, which is the height of this one, and then the width of this stress block. So gamma KUD, gamma is 0.87, we calculated that. Ku is 1, your depth is 526 times 400, which is your width 400. You look at the beam examples where we use this stress block, where we have this area. So simplifications gives this in the newtons, because all the values are in the newton. Then if you just divide by thousands, it give me 5784 kilonewton. So this is the force in the compression region of these sections. Now let's say I like to calculate the force in the steel in the compression side. So first of all, to calculate the stress, we need to know the strain value in this compression zone. And strain in the compression reinforcement is, if I draw the line here, which is the strain in this zone, I can take the ratio, this strain in the steel, which is compression steel, divided by the extreme compression, so that is 0.03 the concrete. So this strain divided by this strain, respectively these dimensions, because this strain has this dimension, let's say. So these dimensions would be taken as this 600 take away 74 will give me this distance 526. So this distance is 526 divided by this whole, which is 600. So basically this strain has this distance, and this strain 0.05 has this. So it's a similar triangle. If you take this triangle and if you take this triangle, this horizontal distance divided by the horizontal distance over the vertical distance, respective vertical distance ratio. So if I want to calculate the strain in the compressive steel, I can just say 526 times 0.03 over 600 gives me 0.00263. So now this strain we need to check it against the yield strength of your steel. Now the yield strength of the steel can be calculated as Fy over Es. So that is the Young modulus of the steel over yield strength of the steel to the Young modulus. Now that is given here in our questions. I can show it to you in the examples. That in the questions we have these 500 megapascals that I substitute here. Young modulus of the steel 200,000. We check this Young modulus in the many examples. That gives me 0.0025, and that's also satisfy the requirement of this maximum strain in the reinforcement, which is 0.0025. We can't take the strain value, the yield strength value greater than 0.025. that is satisfy this condition. So we can just compare what we have calculated. So look at this strain value is 0.00263, which is greater than 0.0025. So in this case, steel is yielded. Steel is yielded means steel reached the yield point. So if the steel reached the yield point, then we say that maximum, this is the 0.00263, but the standard said you should take the maximum 0.0025. So we can't go more than 0.0025. Although it has 0.0026, we need to just take it 0.0025. So the strain in this compressive steel is 0.025. If I know the strain, the stress value for this strain is 500, right? Because if you just multiply this 0.0025, if you want to calculate this stress, 0.025 times the Young modulus will give me this value 500 megapascals. So once you have this 500 megapascal stress times area will give me the force in this steel. So stress times area is 1200 millimeter square, that is given in our example 1200 millimeter square. So I substitute that 1200 millimeter squares gives me 600,000 newtons divided by thousands to get it in the kilonewtons. So this is the stress in the compressive steel. So in the next video we will calculate the stress in the tensions, and then we will calculate the moment at this particular point for the decompression point. So we stop here, and in the next videos we're going to look at the stress in the tensile steel and then moment. Thank you.